So I want to kick things off today with a quote from Alan Kay that, I don't know, it almost feels like a challenge to our whole industry.
Oh, which one?
He said, and I'm paraphrasing a bit, that the internet was done so well, people just think of it as a natural resource, like the Pacific Ocean.
Right, something that's just there. It's always been there.
Exactly. And he asks, when was the last time a technology with a scale like that was so error-free?
It's a profound observation, isn't it? As users, we get annoyed if a page takes, like, 3 seconds to load.
Oh, totally.
But we almost never stop and think about the sheer engineering miracle that makes it load at all.
Right. We treat Wi-Fi like oxygen. But you and I know that underneath that calm, natural resource is this massive, screaming machine of complexity. And that is exactly what we are dissecting today. We're looking at data-intensive applications.
Specifically, we're diving into Chapter 1 of Martin Kleppmann's Foundations of Reliable, Scalable, and Maintainable Data Systems.
Which is, let's be honest, basically the Bible for modern back-end engineering.
It really is. If you've been in a system design interview in the last 5 years, you've probably had this book thrown at you.
Definitely. And Kleppmann's whole point is that the game has changed. For most apps now, raw CPU power is rarely the bottleneck anymore.
It's not. The real limit is the data, the amount of it, the complexity of it, and, the speed at which it all changes.
So the mission for today's deep dive is to get past the buzzwords. We're going to unpack the 3 pillars he talks about: reliability, scalability, and maintainability. And I want to get specific because we all use these words, but they have really strict engineering definitions.
And we're going to see how the lines between our tools are blurring. We used to have these neat little buckets, right? This is a database, this is a message queue, this is a cache.
But now you've got Redis acting as a stream processor or Kafka holding on to data like it's a database. The tools are blending, which means we have to understand the principles underneath.
Exactly. So let's start with that first pillar, reliability.
Okay, so to a normal person, reliability just means it works. But in a big distributed system, working is a surprisingly high bar.
Kleppmann starts with a really important distinction. It's the difference between a fault and a failure.
This is such a crucial mental model. A fault is when one component goes off spec, a hard drive crashes, a network packet gets dropped.
Right. And a failure is when the whole system stops serving the user. And the core philosophy of reliability is, well, you can't prevent faults. You shouldn't even try to get the probability to 0.
Because it's impossible, right? If you have enough machines, faults are a statistical certainty.
Let's just look at the math. A hard disk has a mean time to failure in MTTF of about 10 to 50 years.
Okay, for my single laptop, that sounds great.
It does. But if you're running a storage cluster with, say, 10,000 disks, which is not that big these days, statistics say you should expect 1 disk to die every single day.
Every day. So if your software assumes the hardware is perfect, your system is technically broken every 24 hours.
Correct. And in the old world, the mainframe world, we solved this with hardware redundancy. RAID arrays, dual power supplies.
We tried to make the machine itself bulletproof.
But then the cloud came along. AWS, Azure, and the whole philosophy is different.
Totally different.
Yeah. In the cloud, instances are almost ephemeral. They can just vanish without warning. The platform cares more about flexibility than the reliability of any one single machine.
So we had to shift from hardware fault tolerance to software fault tolerance. We stopped trying to prevent the crash and started designing systems that expect the crash.
Which brings us to the most famous example of this whole philosophy.
The chaos monkey.
The Netflix approach.
I remember when I first heard about this, it sounded completely insane. To make your system reliable, you write a program that deliberately kills your own servers in production.
Randomly, during business hours. It sounds counterintuitive, but think about the psychology of it. If you know a robot might kill your server at 2 p.m. on a Tuesday,
you have no choice but to build your code to handle it.
You're forcing an inoculation. If you don't trigger faults on purpose, that error handling code, the stuff that's supposed to save you,
the stuff that catches the exception and retries,
that code never actually runs until a real crisis hits at 3 a.m., and code that never runs is code that usually doesn't work.
It's the difference between a fire drill and an actual fire. But reliability isn't just about the machines, is it? We have to talk about the most unreliable part of any system.
Us. The wetware.
Yep.
The book cites a study of large internet services that found configuration errors by operators were the leading cause of outages.
More than disk failures.
Oh, way more. Hardware faults were only like 10 to 25% of outages. The vast majority was human error.
Yeah.
pushing a bad config, typing the wrong command.
So how do we engineer around ourselves? We can't really deprecate people just yet.
Well, you build sandboxes, safe places to test things out. But maybe more importantly, you need fast, simple recovery mechanisms.
Rollback.
Exactly. If I push a bad config, I need to be able to undo it instantly. If fixing a mistake is slow or complicated, your system is brittle. And it doesn't matter how many redundant disks you have.
Okay, so our system now survives crashing disks and clumsy humans. It's reliable. But now everyone wants to use it. We need to talk about scalability.
This is probably the most abused word in all of tech. You hear people ask, is this database scalable? As if it's just a yes or no question.
Scalable, true. And we can all go home.
Kleppmann argues that saying X is scalable is basically meaningless. Scalability isn't a feature, it's a question. It's, if our load goes up by X, how much do we have to increase resources to keep performance the same?
But to answer that, you have to define load. And load isn't just one number, like users.
Exactly. You need what he calls load parameters. For a web server, that's probably requests per second. For a database, it might be the read-to-write ratio. You have to know the actual shape of your traffic.
And the book uses Twitter as the case study here, and I think this is the real aha moment of the chapter. It just perfectly shows that you can't design for scale in a vacuum.
The Twitter story is a classic. So to understand it, let's look at their two main operations. First, you post a tweet. That's a write.
Simple enough.
Second, you view your home timeline. That's a read.
And the key thing here is that the volume is totally lopsided.
Heavily lopsided. In the 2012 data he uses, they were seeing about 400 to 600 tweets per second. But reads, people refreshing their timelines, was 300,000 requests per second.
Wow. So as a read-heavy system, we're talking 2 orders of magnitude more reads than writes.
Correct. So imagine you're building Twitter v1. You probably use a normal SQL database. When I tweet, you just insert a row into a global tweets table. It's simple, fast.
Okay, but then I open my phone to look at my timeline.
Now, the database has to do a ton of work. It has to look up everyone you follow, find all of their tweets in that one giant table, sort them all by time, and then give you the top 20 or so.
That sounds like a massive joy-on operation. And doing that 300,000 times a second.
It just annihilates the database. That pull model where you compute the timeline on demand, it just collapsed under that read load.
So they had to switch to approach number 2, the push model, or what they call fan-out.
They completely flipped the architecture. In this model, every user have a pre-computed cache of their timeline, like a little mailbox. When I tweet, the system doesn't just write to one table. It looks up all my followers and pushes my tweet into their individual mailboxes.
So the hard work is done on the write, not on the read.
Exactly. Reading your timeline becomes instant because it's already built. They just shifted all the work from the read side to the write side.
But wait, there's got to be a catch. This works fine if I have 100 followers. The system does 100 writes, no big deal. But what about the Justin Bieber problem?
The celebrity problem. The technical term is skew. If a user with 30 million followers tweets, the system suddenly has to do 30 million writes to 30 million different caches.
And it has to be fast, right? A tweet can't have a 5-minute delay.
Precisely. Trying to do 30 million writes in a few seconds creates this enormous write spike. You could grind your entire backend to a halt just because one person tweeted good morning.
So let me get this straight. Approach 1, the pull model, breaks on reads. Approach 2, the push model, breaks on celebrity writes. So what did they do?
They used a hybrid. And this is the key takeaway. For most users, Twitter uses the push model. Tweets are fanned out. But for celebrities, they switch back to the pull model.
So if I follow Justin Bieber, his tweets are not preloaded into my mailbox.
No. When you load your timeline, the system grabs your normal pre-computed feed, and then at that moment, it fetches and merges in the tweets from any celebrities you follow.
That is fascinating. So there was no single magic scaling sauce. They had to build this custom architecture that was specific to the statistics of their user base.
Exactly. If every user had the same number of followers, they wouldn't have needed it. Scalability is always specific to your application's constraints.
Okay, so we've scaled. But how do we know if it's working well? We usually talk about averages, right? The average response time is 200 milliseconds.
And Kleppmann basically says to stop doing that immediately. He calls it the flaw of averages.
Why? I mean, 200 milliseconds sounds pretty good.
Because the average hides the truth. A 200 meters average could mean everyone gets a 200 meters response, or it could mean most people get an instant response, and a few unlucky users are waiting 10 seconds.
The average just smooths out the pain.
It does. It doesn't tell you how many of your users are furious. So instead, you have to look at percentiles. The median, the P50, tells you the typical experience. But for big systems, you care about the tail, the P95, P99, or even
The
P99.9.
T99.9, so that's the slowest 1 in 1,000 requests. I have to play devil's advocate here. If 999 users are happy, why do we pour so much effort into that one slow experience?
Amazon has a really good and slightly terrifying answer for that. They found that the customers who get the slowest requests are often the ones with the most data in their accounts.
Ah, meaning they have the biggest order histories, they've bought the most stuff.
Exactly. They're your VIPs, your whales. If you ignore the P99, you are systemically giving your best, most profitable customers your worst experience.
That is a brutal realization. And the book mentions the financial impact is real, right? A 100-millisecond delay cost Amazon 1% in sales.
It adds up fast. But there's another, more technical reason to be afraid of the tail. It's this concept called tail latency amplification.
Okay, that sounds like a sci-fi weapon, but the math behind it is terrifying for anyone building microservices.
It really is. A modern web page isn't just one call. When you load a product page, the back end might make 100 different calls to different services for pricing, inventory reviews, recommendations.
Right, it's a scatter-gather. You ask everyone at once.
You do. But here's the problem. If each of those 100 services has just a 1% chance of being slow,
Then the chance that the whole page is slow isn't 1%.
no, it's much, much higher. Because the final response is blocked until the slowest of those 100 services finishes. If you roll a 100-sided die 100 times, you're almost guaranteed to roll a 1 at some point.
This is head-of-line blocking. That one slow service holds up the entire response for the user.
Exactly. So in a complex system, the outliers stop being rare. They become the thing that defines your user's experience.
Wow. Okay, so we've covered reliability and scalability. Now we have to talk about the long game. The unsexy hero of software, maintainability.
Kleppmann makes a great point here. Most of the cost of software isn't the initial development. It's all the ongoing maintenance.
Fixing bugs, keeping the lights on, investigating failures, adapting it to new business needs.
And if you don't design for that from the start, you are actively building what engineers call a big ball of mud.
I think we've all inherited a project like that, where you touch one line of code over here, and for some reason, the user's profile picture disappears over there.
The spaghetti code nightmare. So to avoid that, the book gives us 3 design principles. The first is operability.
Which is really just be nice to your operations team.
It is. It's about visibility and control. Can I easily see what the system is doing? Is the monitoring good? Does it have sensible defaults? A maintainable system should be boring to operate.
The second principle is simplicity.
Now, this one is tricky. Simplicity doesn't mean the problem you're solving is simple. It means you're managing the complexity well. Kleppmann talks about the difference between essential complexity and accidental complexity.
This is such a key distinction. Essential complexity is just the difficulty of the problem itself. Like if you're building tax software, the tax code is complicated. You can't just wish that away.
Right? That complexity has to live somewhere. But accidental complexity is the complexity we, the engineers, create ourselves. It's complexity in the implementation, not the problem.
Like using 5 different microservices when one simple script would have done the job.
Exactly. And our main weapon against accidental complexity is abstraction.
Hiding the messy details behind a clean interface.
Think about SQL. It is a beautiful abstraction. It hides the physics of the spinning disk, the B trees, the memory management. You just say, select star from users.
You focus on the what, not the how? A good abstraction lets you reason about the system without needing a PhD in computer hardware.
But, and this is a huge but, you have to choose the right abstraction.
No.
If the abstraction is leaky, if the messy details keep popping up and biting you, it actually makes things more complex.
Which brings us to the third principle, evolvability.
Or sometimes you'll hear plasticity or expensibility.
Yeah.
It's just accepting that your requirements are going to change. Twitter had to move from approach 1 to approach 2. They had to change the engine while the plane was in the air.
And a maintainable system is one that lets you make those changes without being terrified. If your code is a ball of mud, you're too scared to change anything because you have no idea what might break.
And this is where things like good tests, agile workflows, and proper schema migration tools come in. Evolvability is just the ease with which you can adapt to the future.
So bringing this all together, reliability, scalability, maintainability, they aren't just buzzwords you put on a slide. They are real and often conflicting engineering trade-offs.
They absolutely pull against each other. That's the hard part of this job. Making a system more reliable by adding redundancy might make it more complex, which hurts simplicity and maintainability.
Or making it super scalable, like Twitter's fan out, might introduce weird delays that hurt consistency.
There are no easy answers, only choices. The best architecture depends entirely on your load, your users, and your needs.
And the implication here is pretty huge. It used to be that only, the Googles and the Amazons of the world really had to think this hard about this stuff.
But now, with the cloud, distributed systems are becoming the default. Even a small startup's app is built on AWS with queues and caches and serverless functions.
So that means every developer, even if you're just building an MVP, needs to start thinking like a data system designer. You can't just write your code. You have to understand how the data is flowing through the pipes.
That's right. You have to know what's happening under the hood. You can't treat the cloud as just a magic infinite computer anymore.
And that actually leads me to a final thought I want to leave everyone with. We talked about how much we love abstractions, right? SQL, S3. They simplify our lives. We treat them as black boxes.
We do. We trust the box.
But what we learned today is that inside those black boxes, there are huge architectural differences. So if we treat a database as just a magic box for data, without understanding the difference between fan out and tail latency, are we setting ourselves up for a failure we won't know how to debug?
That is the danger. Abstractions are amazing until they leak. And if you don't have a mental model of what's happening inside that black box when the load finally spikes, you won't know which lever to pull. You'll just be pressing random buttons on a machine you don't understand.
So to everyone listening, take a look at your own systems today. Don't just ask if it works right now. Ask yourself, is my system a library or is it a mailbox? And what happens if the load increases by 10x tomorrow? Thanks for diving in with us.
It was a pleasure. Keep asking those hard questions.